All right. We have a few questions that people posed earlier today. One left over from Lecture 1.4. Question was, in question number 3 of this pretest questionnaire, the first and third options seem to point to the same concept of all the events resulting from an exponential behavior, owed to them being stochastic events that are controlled by the laws of probability. Please explain. Well, option 3, I said something like different probabilities based on different circumstances. That really is not realistic. Basically, when you have an event, a stochastic event that becomes deterministic, when you have a large number of these events, the probability is going to be independent of what else goes on. And in particular, when we talk about radioactive decay, the probability that a radioactive nuclide is going to decay is independent of temperature, pressure, phase of the moon, whatever. The probability that a photon beam is going to be attenuated is going to be a function of some of the properties of the attenuator, but it has nothing at all to do with the temperature, pressure, phase of the moon, etc. So the probability is going to be the same regardless of what the external conditions are. The probability of attenuation, for example, is going to be a function only of the energy of the incident photons and of some of the properties of the absorbing material, like its atomic number, like its electron density, and we'll go into some of these things later on in the semester. Okay? I hope that closes off the first part of the course, the first 4 lectures. For the next 4 sessions, we're going to talk about how we produce radiation. Today we're going to be talking about what the various mechanisms are for producing radiation. We're going to do some of the math in the next session. Then we have 2 sessions on production of X-rays. So, someone asked the question, can you please elaborate on what is a branching ratio for radionuclides of decay via both electron capture and positron emission? Someone want to try to answer that? What's a branching ratio, first of all?
Just what fraction of the time it undergoes each type of decay?
What fraction of decays are going to go in one branch versus another branch? Correct. So what would the branching ratio be for electron capture versus positron emission?
Does it depends on the nucleus, the mass of the nucleus?
Sure,
and
sure.
Some other stuff.
Yeah. And you're not going to have to memorize that kind of stuff. That's a number you can look up in tables. But yeah, it's going to depend on the particular radionuclide. If the radionuclide is proton-rich, it'll decay in one of 2 branches. One branch is via positron emission, provided there's that 1.02 MeV energy difference. Or the other branch will be electron capture, and that is going to occur regardless of what the difference is in energy levels. Okay, what are the differences and similarities between mass defect as it relates to binding energy and radioactivity? Someone want to try to answer that one? What is the important thing regarding the energy in a radioactive decay? What do we look at? Yeah, Bridget.
The energy of the products would be lower than the energy of or like the original.
And how do we get this energy? How do we determine what the energy is?
Like from the mass.
From the mass, right.
Binding energy.
We have determined the mass of a radionuclide, determine the energy equals mc squared, determine it for the parent, determine it for the daughter. If there's a difference, if the daughter energy is lower, then we're going to have some kind of decay event occurring. Which event? It all depends, and we go into those when we look at the various events. Is there such a thing as medium mass nuclei? I guess one of the questions had an option: small nuclei, large nuclei, or light nuclei, massive nuclei, and in the middle were medium mass nuclei. Well, whether we say something is a heavy nucleus or a light nucleus really depends on the problem we're looking at. You know, for example, if we're looking at spontaneous radioactivity, these occur in large, heavy, massive nuclei, generally above the atomic number of lead, 82 or something like that. If we are looking at heavy ion radiation therapy, well, a heavy ion could be as large as a carbon ion, 6 protons, 6 neutrons. But from the point of view of radioactive decay, that's a light nucleus. So everything is really relative. It depends on the particular circumstance, the particular problem you're looking at trying to solve. Okay? When a nucleus absorbs a photon with energy greater than the binding energy, what happens to the photon's excess energy? Who would like to answer that one?
Does it go to the products of the reaction?
It goes to the products and in what manner?
Kinetic energy.
Kinetic energy. For example, let's look at oxygen-16 being hit with a photon, energy greater than about 10 MeV. It forms oxygen-15 plus a neutron. So if we have a lot of energy, excess energy, that energy is going to go into kinetic energy. How do you think that's going to be distributed?
Relative to the mass.
According to the mass. So does the massive particle get more or less energy? Thaddeus? Less. Why? What physical principles are involved in that?
Conservation of momentum.
Conservation of momentum and conservation of energy, of course. So in fact, you're going to determine how the kinetic energy in alpha decay is distributed among the radon nucleus and the alpha particle. And it's kinetic, it's just using your conservation laws. Makes it a pretty straightforward problem. Okay? Are there any other questions before we start on concept test questions? Okay, good. Let's see where we are. This is 2.1. Okay. In a radioactive decay process, the mass of the products is greater than, less than, or the same as the mass of the parent nucleus. Everyone have their cards? Okay. Essentially, everyone got that one right. The mass of the products is less than. Okay? So, you determine the mass of the parent, you determine the mass of the products. What happens to the difference in mass? That's energy. And that's the energy that's emitted in the form of in the radioactive particle. Okay? Next question. In an alpha decay process, I'm sorry, Mary.
Can I ask a question about the last one?
Sure.
So my question was regarding the difference between mass defect for the case of decay and then the case of like binding energy.
Okay.
And so for decay, the sum of the products is less than like the sum of the parent.
Right.
But then
Some of the masses of the products.
yes. Mm-hmm.
Right. When we look at mass defect, for example, we're trying to determine the binding energy. So once we've determined the binding energy of in a nucleus from the mass defect, we can determine what energy of, say, incident photons is going to be necessary to cause photodisintegration. And we'll see that later on in the course. We'll see that's one of the processes by which X-rays and gamma rays interact with material. and what consequences that has.
I guess I was confused because like the mass of, I feel like in one case we have where the energy of the products is greater, and in the other case the energy of the parent is greater for the two scenarios.
Okay, so in the case of mass defect, we determine the mass of the individual particles that make up the nucleus. We then determine the mass of the nucleus. The mass of the nucleus is going to be less than the mass of the individual particles. The difference in mass converted to energy is the energy that holds this nucleus together. Okay? Okay, good. Okay, back to alpha decay. In an alpha decay process, A, kinetic energy is approximately evenly divided between alpha particle and daughter nucleus. B, most of the kinetic energy goes to the alpha particle. And C, most of the kinetic energy goes to the daughter nucleus. Okay, we have diversity of opinion. Let's talk about it.
Not much diversity. It's just concepts. Yeah, he did.
Because if it has like a larger mass, not as much like kinetic energy. Like if you were to like put the same amount of like force on something that is less, it's going to have more kinetic energy. So it's like the alpha particles get a lot lighter than the nucleus, so it should have more kinetic energy.
Okay, yeah. I just got them backwards.
I think you were thinking of total energy instead of kinetic.
No, I just got them backwards.
Okay, let's vote again. Okay, please hold up your cards. Okay, everyone got it right this time. Most of the kinetic energy goes to the alpha particle. Again, it's conservation of energy and conservation of momentum. When we work out the numbers, it turns out that the ratio of energy is roughly proportional to the ratio of masses. Not quite, but close to it. So if we're looking at, say, alpha decay of radium-226 to form radon-222 plus an alpha particle has a mass of approximately how many atomic mass units?
4.
4. Radon-222 has a mass of approximately what? 222. That was a difficult problem. So it's roughly 4 to 200. Roughly, what's it? 4 to 200 in terms of the kinetic energy. So what we normally do is we say that radium gives off an alpha particle. Mass defect is 4.71 million electron volts. To a first approximation, it goes into the alpha particle. The second approximation we could go a little bit more exact, but roughly speaking, it goes to the alpha particle. Okay, next question. The therapeutically useful radiation emitted in the radioactive decay of cesium-137 comes from A, emission of a characteristic X-ray resulting from an L to K transition in barium-137. B, emission of a gamma ray from an excited state of barium-137. Or C, the 0.51 MeV beta particle emitted from the beta decay of cesium-137. Where do we get the useful radiation? Hold up your cards, please. Okay, let's talk about this one.
Does anyone remember?
gamma rays, right?
And then they will come at the same energy like 1.3.
And
So average is 1.25.
I
That's
don't
two
like
energy
it.
levels, it takes
I
down
don't
to
know.
two energy levels. And then it's gamma.
Average is 1.25.
Yeah, it decays back to two energy. When it decays down, that's gamma.
I think.
Okay, let's vote again. Okay, let's see. Vivian, you chose B. Why did you do that?
It how do I say this? Like in the products, it has. I remember it having two gamma rays, and one energy is like 1.33, and the other one is like 1.30. The different, I mean, the average in that is like 1.25. Just remember that it was just the emission of the gamma ray. That's
Okay, but you're
useful.
thinking of a different radioactive material.
Am I really?
You are.
Oh, what is that?
Did someone help her?
Cobalt-60.
Cobalt-60, right.
Darn.
But, all right, so, but,
Oh, close enough.
all right, but let's talk about cesium-137. You're on the right track, though.
Okay.
How does, what's the decay mechanism?
Like a positron. Someone help me out.
Someone help her out?
It's an isomeric transition.
No. Arvesh, what do you think it is? Bridget, how about you? No idea, okay. All right. Cesium-137 has too many neutrons. Okay, so what mechanism do we have when we've got too many neutrons? Beta decay, correct. So we can look at it kind of as a neutron turning into a proton plus an electron. The electron is ejected. So cesium-137 decays to form barium-137, giving off a beta particle of about 1/2 MeV. But is that the therapeutically useful radiation? Humberto, you said no. What is the therapeutically useful radiation?
The gamma ray
From?
from the transition to the excited state.
Correct. Okay? So what happens in the case of the decay of cesium-137, we have a beta given off, we wind up with an excited state of barium, and it's this excited state of barium going into the ground state that gives off a gamma ray that we use for radiation therapy purposes. Okay? Why don't we use that beta for radiation therapy?
Doesn't travel too fast.
Doesn't travel very far, right. If you have a bare cesium-137 source and you say implant it into a patient's tumor, you'll wind up delivering a very high dose to the right at the source, and that's about it. Okay, so we need some more penetration, and it turns out that the gammas provide us with the appropriate penetration. Okay, so the answer is it's only the gamma ray that's sufficiently energetic to be therapeutically useful. Okay? Next question. In beta decay, the energy of the beta particle is less than the transition energy of the interaction. Which statement is true? A, energy is not conserved in this interaction. B, the remaining energy goes into kinetic energy of another particle. C, the remaining energy is converted into mass of the proton. Okay, commit yourselves to an answer. Okay, let's talk about it.
I guess like all of the kinetic energy goes into the beta particle. or anti-neutrino.
Yeah.
So that's why I chose beta.
It's in the
always conserved.
Yeah, it's
Yeah.
conserved. It can't be A and C. I don't know what that really means.
Yes.
Protons, you're not making protons at all.
So.
And only like, if you remember, only a very small or like little amount of kinetic energy goes into the recoil, which I don't know what that is. Oh, yeah. A recoil nucleus.
Okay, do we want to try to vote again? Okay, Daniel, you say it goes to another particle. What's the other particle?
The
The anti-neutrino. That is correct. So, the decay produces an anti-neutrino which carries off the additional energy. Again, we've got to conserve energy, regardless of what happens. But in the case of beta decay, some of the energy goes into the anti-neutrino, the rest goes into the beta, and we really wind up with a whole spectrum of energies coming off the beta decay. Keep in mind again, a single beta decay is a what kind of process? Say it. Stochastic. When we look at a large number of beta decays, we have a spectrum which is deterministic. Very good. All right. Let's look at cobalt-60. Cobalt-60 is a particularly desirable isotope for external beam radiation therapy for all of the following reasons except A, the mean gamma energy of 1.25 MeV is reasonably penetrating. B, 2 gamma rays are emitted for each decay, resulting in a greater specific activity. C, cobalt-60 has a sufficiently long half-life that corrections never have to be made for radioactive decay. Okay, cast your ballots and talk about it.
Yeah. I'm gonna put some piece of what I explained 2 questions ago.
I know that in beer.
I need to say,
So there are
Like
generators,
5 points.
It's large.
Yeah.
But for treatment, it's like long enough.
Right.
So the fact that
It's not long enough.
we sort of normalize like
It's not long enough to never make
Yeah.
changes.
activities about it.
It's also normalized to mass.
Okay, that's what I thought.
Yeah.
So I don't know how
I knew where that 1.25 came into play.
you're looking at specific activities, disintegration per
Oh, it's close.
mass. Per mass per second.
Well, cobalt-60.
Well, it might be defined as not as disintegration, but as
As
radiation emitted.
yeah,
Isn't it?
that's what I think. Yeah. I think you're right.
Okay, let's vote again.
Cobalt starts to change.
Okay, Wenhua, you said C. Why did you say C?
Cobalt-60 half-life is not that long,
Do you recall what it is?
5 years.
5 years, right. So as a result of this 5-year half-life, you have to make corrections for the decay of cobalt about once a month. It's about, that turns out to be about 1% per month. Okay? Now, when I first got into the field of medical physics, no, I was not a contemporary of Röntgen. Cobalt-60 units were used quite a lot in the US. It was just about the time that linear accelerators were starting to get popular. Nowadays, we've pretty much replaced cobalt units, except for the gamma knife, which still uses cobalt sources. You'll find cobalt teletherapy units still in some developing countries. So they're still around. But you've got to replace the source, typically about every 5 years. In fact, there's a great story. I'm not going to digress to tell you about the story. about the race to develop a cobalt teletherapy unit. It was MD Anderson versus the group in Saskatchewan, Canada. The guy in Saskatchewan was Harold Johns and Cunningham, same guy. At MD Anderson was Gene Grimmett, who was the physicist there. Unfortunately, they beat us. Peter Almond, who is a former faculty member here, has a real good book about the race to build a cobalt teletherapy unit. I think we've got a copy in our library. Okay. In positron emission, a proton, where's this? Oh. In positron emission, a proton can be looked on as decaying into a neutron plus a positron. The mass of the neutron plus the mass of the positron is greater than the mass of the proton. How is this possible? A, the additional mass comes from a neutrino. B, the additional mass comes from energy that must be added in order for the decay to occur. And C, the mass of the parent nucleus is greater than 1.02 MeV more than the mass of the daughter nucleus. So how do we get positron emission? Okay, hold up your cards. Okay, let's talk about it.
So yeah, so does it come from somewhere else? Or is just
I think I remember that just being a requirement of positron
so that's probably physically is it? I guess that was.
You don't have to put it in, it's just,
Okay.
yeah.
So there's this idea of like an energy threshold, right?
I think it's could be mostly because of what he said in the lecture.
The mass of
defect.
Yeah.
Does that ever prevent the nucleus from decaying if it, why can't it just always be mass? So if it was something wrong.
Yeah, you call it transition.
Right, okay.
Okay.
Although there's no transition word in there, but.
Okay, hold up your cards. Okay, Bridget, you changed your mind. Why?
I'm still not totally sure on this one, but with positron emission, you you need like the mass of positron plus the mass of the electron, so it's like 1.02 MeV. So you need that much more energy.
Okay, so you need some additional energy, which comes in the form of a difference in masses between the parent and the daughter. That difference in mass has to be at least 1.02 MeV for positron emission to occur. If it's less than 1.02 MeV, you're just not going to have the process occurring. Okay? Let's talk a little more about positron emitters. Positron emitting radioisotopes are most likely to be produced in the following manner. A, in a cyclotron, B, in a nuclear reactor, or C, positron emitters are naturally occurring. Okay, hold up your cards. Okay, let's talk about it.
Yeah, I'm not sure.
Is it's not nuclear reactor, because I recall that's like beta decay, right?
Yeah, it's not.
So we can do yeah. So
Yeah,
that's
that's-
rewrote that one out and see.
I don't know, like,
I don't know if
there's
it's
another mechanism.
So to have that.
So it's not naturally occurring.
Right.
So it's in the.
The reason it's a cyclotron, not a reactor, is because a reactor is like you get neutron hot
They're
particles.
really
But
cool.
it's possible
Yeah.
to do things that are positive for proton heavy.
It's huge, right? And they use a lot of like energy,
Cyclotron
right?
usually will
Or
react
power.
protons inside.
It's like they're huge. Yeah.
They just like accelerate it.
I've never seen one before.
They're cool.
Yeah.
Okay, want to vote again? Okay, everyone got this one right. Positron emitting radioisotopes. What do we know about the relative ratio of protons to electrons? To neutrons, rather.
They're proton rich.
Proton rich. So if we want to produce a positron emitter, we take some neutral nucleus bombarded with protons. How do we produce the protons? In a cyclotron. Why don't we use a cyclotron to produce beta emitters? Emily, why don't we do that?
I'm not sure.
You're not sure. Mary?
Does it have to do with the relativistic effects?
How would we produce a beta emitter? What do we know about the relative ratio of neutrons to protons?
You would have too many.
Too many neutrons. So we'll start with something stable, add neutrons to it. How do we produce neutrons?
Reactor.
In a reactor, correct. We can't produce neutrons in a cyclotron because, why? They're not charged, exactly. So we need to produce the neutrons in a reactor. We put a stable material in the reactor for a certain period of time. It gets bombarded with neutrons. It then becomes neutron rich, and then it decays via beta decay. Okay? Good. All right, we've got some hypothetical radioactive materials. We've got Houstonium-84. Has 43 protons and 41 neutrons. It decays to form Dilithium-84, which has 42 protons and 42 neutrons. The mass of the dilithium nucleus is 0.67 MeV less than the mass of the Houstonium nucleus. Which decay process is most likely to occur? A, beta emission. B, electron capture. C, positron emission. D, B and C. Okay, we have a variety of opinions. So let's talk about it.
Okay, so I think
So
B
it's
and
converting a
C
proton
work
to a
based on
neutron, so
the
it has to gain
number of
an
protons and
electron
neutrons, which
as a
it's the
charge.
energy that I wasn't
So
sure
it
about.
can either do
So you're
electron capture or positron.
Dropping one proton and adding a neutron.
Right.
Okay.
So you can either do that by capturing an electron to produce like a neutron,
Positron emission, you have to have that 1.02
or
MeV mass decay.
Okay, in beta
So if
decay,
there's only 0.6 difference, you don't have enough
beta is
extra energy to form a
neutron decreasing by
Yeah.
1,
Decreased by 1.
and positron, or I mean, proton increasing.
So it's opposite. Oh, it's an opposite.
yeah, beta's opposite. So
Okay, let's
I
vote.
think B and C makes sense for the numbers, but I don't know about the energy effect. I think the 0.67 is important. Yeah, I think it's B. It's a positive.
Okay, Halavani, you chose B. Why?
Initially I chose B because it's the energy here mentioned is 0.67,
Mhm.
and for a positron emission to occur, it should be 1.02.
Okay.
So should we be?
Why is it not A?
Because it's
Because it
Vivian,
has,
go ahead.
it has one less proton and one more neutron.
Correct.
And it's actually the opposite.
For beta.
Yes.
So Houstonium is proton rich, it's got too many protons, so it's got to decay in some manner that gets rid of the proton. And there are two ways to do that. There's electron capture, there's positron emission, but the mass of the dilithium nucleus is only 0.67 MeV less than the Houstonium nucleus, so we don't have enough of a mass difference for positron emission to occur. Therefore, the only thing we can do, you can have is electron capture. Have that? Good. Radioactive nuclei that decay via electron capture are particularly desirable for implant radiation therapy because A, the characteristic X-rays are typically attenuated within the patient. B, the short half-lives of these nuclides result in short periods when the patients must be isolated. C, these materials are relatively easy to produce. Okay, well, you got it all right. The characteristic X-rays are in the range of a small number of keV, 20 to 50 sounds reasonable. A good example of a radioactive material that decays, giving off characteristic X-rays, is iodine-125. We use iodine-125 for implant therapy. And the nice thing about iodine-125 is you implant the seeds, these seeds, and the patient's body attenuates a sufficient amount of the radiation, so there is no radiation safety hazard. Now, if that were not the case, if the radiation were more penetrating than it is, iodine-125 has a half-life of something like 60 days. So the patient would have to be in isolation for a long period of time. But fortunately, because of the lower energy of the characteristic X-rays, and energies of 20 to 50 keV are typical. Palladium-103 is another example. You can implant the sources into the patient as long as it's fairly deep within the patient, and then let the patient go home when it's medically acceptable. Okay? All right. Which of the following is the useful radiation from the decay of fluorine-18? A beta particle of energy 1.71 MeV. B, a characteristic X-ray of energy 35 keV. C, a gamma ray of energy 140 keV. D, two gamma rays of energy 511 keV each. Okay, let's talk about it.
I don't know.
It's because it's used for deoxyglucose. So,
That's what I thought, but
okay.
I don't know.
Was it?
Yes, it's used for PET.
That's a cyclotron produced isotope. Yeah. You have to make it.
stabilized, so it's like fluorine like that, or 17 or something like that.
Okay, let's vote again. Okay. Garrett, tell me about the decay of fluorine 18.
It's a positron emitter.
Good.
So it's used in PET imaging in like fluorodeoxyglucose. And
Good.
so when it emits the positron, it annihilates the electron and it produces the back-to-back 511 keV gamma rays. And you can detect that in the PET detector, like the ring detector.
Okay. So that's basically how we use fluorine 18. It's a positron emitter, but we don't do anything with the positron. We take advantage of the fact that a positron will annihilate an electron, giving off two gamma rays, 511 keV each, going off at 180 degrees from each other. And if we can detect two of them using coincidence detector, we know along what line the positron emitter is located. We do it around a ring, so we have a lot of gammas being given off, and then we can determine the spatial distribution of the positron emitter. Okay? Two gamma rays of energy, 511 keV each. And that's it for today. Please turn in your homework assignments. Actually, I have another 15 minutes to turn them in. I presume you have them done by the time you get into class. And have a good weekend and talk about mathematics of radioactive decay, radioactive processes on